which implies basically that y is equal to k over x. I mean, technically plus or minus that, but the different values of k. So, you know, that's it. And then so like, what do those look like? Those are reciprocal functions. So like for k positive, you got one of these guys, right? There's like k greater than 0, something like this. And then I'll draw the other ones in red. K negative, got these guys. But as you can see, even from my crude picture, those are going to meet the given family perpendicularly. So this is what are known as orthogonal trajectories. You can find the orthogonal trajectories for a given family of curves. Standard problem. You guys gonna get this one to put on the test? What are the steps? It's really not that complicated. First of all, step number 1, find dy dx for your given family. Step number 2, take the negative reciprocal of whatever defines dy dx. So flip it over, add a minus. Step number 3, solve the new differential equation. There's your orthogonal trajectories. That's all there is to it. That's what I just did. And step number 4, I suppose, check your answer. Does it make sense? You know, it's always that. You know, I spent money on this sticker because I'm hoping it serves a purpose. This is to try to help you. I thought this might help. I have not as many questions as I was hoping for, so I figured by making this annoying sticker, it might precipitate some questions from my classes. I'm not sure yet. It's my first day. I've really unfurled this sticker upon you, and this is. I mean, this is. See, I can't even properly display it for you guys. I know this is awkward. What can I do? I'll just have to trust you guys to ask good questions, and I'll try not to bully you with my picture. Okay, so while I got this out here, let's just look at a few more examples. Oh, come on. You know, it's funny. You actually have to be able to see it to look at it. Take your time. It's not like we're waiting. We have 12 minutes, right? All right. So what I want to do with the remaining 12 minutes is just to try to showcase some examples from my notes. Next time what I'll do is I'll try to work another application or two probably, but I probably won't take the whole class next time. There should be time if you have a question in particular about some of the homework for next week. You should be able to ask something next class if you have a particular question. I haven't posted the homework yet, have I? For next week? I don't think I did. Not yet. So hopefully I'll do that later today. And then hopefully I'll start talking about how to differentiate functions of a complex value, like a little bit on complex variables and functions. Not complex analysis per se, but kind of like the easy case when you have a function of a real variable, but it's taking its value in the complex numbers. Like we need to develop some basic facts about that. In fact, that material is way easier than what we're doing right now, so you should welcome it. Okay, so here's an example. I did minus bv earlier today. So example 9 actually has minus bv squared. Here's how that works out. You end up with the velocity is like a reciprocal of the time. And again, as time goes to infinity, this goes to 0, right? But it's kind of funny. In this case, if you calculate the position as a function of time, you get a log. So in fact, the position is, looks like it's not bounded. I don't know. That's weird. Yeah. Oh, Luke, question? Oh, okay. So here's an example. Here's Newton's law of cooling. Maybe you've seen this in another class. You guys see Newton's law of cooling in another class yet? Which class did you see it in?
Probably, I think Skimor just showed it to us briefly in Cal 2.
Cal 2? Yeah, that's appropriate. It's a good problem because basically you look at what kind of problem is this? Like, look at that. dt equals k plus kt equals kr. Well, that's a linear first order differential equation. That's like made to order integrating factor problem. that's interesting, right? Because like it describes how the temperature changes for like a cooling cup of coffee in terms of what the ambient temperature and a particular constant that relates how quickly the system loses temperature, right? Or heat, really. So it's a very natural equation, right? It says basically things cool down faster when their temperature is further away from the room temperature. So it's not, basically here's the fundamental equation up here. dt is minus k times t minus r. I mean, there's various labels you can put here, the k and the r or whatever. Here I've chose k to be positive, and r is the room temperature. So like, for example, this is kind of interesting because this is, if you look at this, right, Newton's law of cooling problem, it's not really solving a specific differential equation when it's presented in this way. If you think about it, if k changes, right, you have different differential equations. Every different value of k gives you a different differential equation to solve. And that's why Newton's laws of cooling problems need not one piece of data, but two pieces of data, even though it's a first order problem. Like, you can think about it this way. One of the pieces of data fixes the k, the other one fixes the initial temperature. So anyway, so like this one, I give us that the initial temperature is 150 degrees, and at 1 minute, it's cooled to 120 degrees. I tell us that I also need to, there's actually three things we need. You need three pieces of data, I should say. You need room temperature and you need the ambient temperature and two temperatures, for example. Or you could just have three temperatures. From three temperatures in Newton's law of cooling, you could figure out the room temperature. That's kind of weird, right? Think about that as an experiment. You have a cup of coffee. You take the temperature of the coffee at 3 different times. If you assume Newton's law of cooling applies, you can figure out what the room temperature was just from studying how the coffee temperature decreases. It's kind of a funny little problem. Okay. Anyway, so the solution is really simple. It's like room temperature plus some constant times e to the minus kt, and then you just have to do algebra to fit the r and the k. All right. This one ends up being 70 plus 80 times e to the t log of 5/8. Of course, as t goes to infinity, that's a negative value, right? Natural log of any number less than 1 is negative. And so this goes to 70 as time goes to infinity. Of course, everything goes to room temperature eventually, is the point, right? I don't know, Newton's law of cooling is a neat little problem. But honestly, if I do that on the board, it eats 20 minutes and you don't get much out of it, right? So the orthogonal trajectories you need to see me do on the board. That's important. So I put this silly thing away for that. Let's see here. There's a fun conceptual question there. Suppose you decide to have coffee with a friend. You both get your coffee 10 minutes before the end of a serious presentation by your petty boss, who will be offended if you start drinking coffee during his fascinating talk on maximal efficiencies for production of widgets. You both desire to drink your coffee with the same amount of cream, and you both like coffee as hot as possible. Your friend puts creamer in immediately and waits for the talk to end. You, on the other hand, think you'll wait to put the cream in at the end of talk. Who has the hotter coffee and why?
I'd say the second person because the cream might cool it somehow. I'm not sure.
We're assuming that the cream is thermally isolated too, to be clear. Like the cream is not raising in temperature to room temperature. The cream has the same cooling effect before or after.
Well, if you cool quicker when you're further away from room temperature, then you would want the coffee to be cooler earlier.
That's right.
Yeah.
That's right. You put the cream in as soon as possible to keep it hot as possible, as long as possible. If you're going to put the cream in.
Ninth grade, I think.
Oh, really?
Teacher.
Yeah.
We did a whole lab on it. It was interesting. We actually put creamer in.
And you observe this.
Uh-huh.
Cool. Yeah, I have seen that as a problem in differential equations books, and like a page of math given to explain it. But I don't think it's necessary because as you develop an intuition for what a differential equation means and what it says, you should be able to argue in this way. I think it's also important not to do math where no math is needed. Math should be used where it's needed. I don't think math is needed to make the point you just made. I mean, you could, of course, supplement that with actually working through the general solution to a Newton's law of cooling problem. And there are certain math majors who wouldn't believe you until you did. Anyway, but you guys are not math majors, I don't think. There's still time, right? There's like a math double major, not much. All right, anyway, so here's another problem. Voltage dropped across a resistor, and you also have an inductor. The voltage on the inductor is given by L di dt, right? Inductors oppose the change in current. The voltage on an inductor is proportional to the change in current. That proportionality is the inductance. And so you do Kirchhoff's voltage law around a RL circuit, and you get this. E minus IR minus L di dt equal to 0. And so you have this equation. Look, again, a linear first order ODE. That's an RL circuit problem, right? So you can solve that by the integrating factor. So, I don't know, looking for physical significance of the integrating factor again, it's E, in this case, it's E to the RT over L. So it has some significance. It has something to do with the time constant I mean, it's something like E to the T over time constant for an RL circuit, if you know what that is. If you don't, it's cool. But a time constant for an RL circuit's basically like its lifetime. After 5 time constants in an RL circuit, everything that's happened is going to happen, it's happened. So, like your time constant is about 15 years. You know, I guess it depends. I mean, I'm being optimistic. Maybe you do something interesting when you're 70. You know, so if you want to be more pessimistic, I could say your time constant's 5 years. I don't know. If you don't do something by the time you're 25, forget it. That seems too pessimistic. I don't know. Anyway, you solve this thing with the integration factor technique, and this is your current as a function of time in terms of the initial current, the voltage applied, the resistance, the inductance, and so forth. And if you look at the math here, it's exactly what we did the last week, integrating factor technique with letters. Here's the mixing tank problem. I'll talk about that next class. Here's another mixing tank problem. We'll talk about that next class. Because you guys are what, mostly industrial and mechanical? So we should spend a little bit more time on mixing tank problems this time than I usually do. Here's the logistic growth problem we talked about. Here's a problem I'm fond of. Suppose raindrop falls through a cloud and gathers water from the cloud as it drops towards the ground. And the mass increases as it falls, right? So it keeps gathering water. And suppose that the water, it gathers proportionate to the mass. So like when the mass is twice as big, it's gathering water twice as fast, all right? According to some proportionality constant K. In this case, you don't have, so that's the force minus mg, gravity falling, right? But you don't just have m dv dt because the m is not constant. So now you have dm dtv plus m dv dt. This is what's playing the role of ma in such a variable mass problem. This is a variable mass problem. So then that gives you this differential equation. And you can separate variables, I believe. Or wait a minute. No, it's an integrating factor technique problem again. Sorry, these are all integrating factor techniques. How boring. I mean, fascinating. And then so integrating factor at this time is e to the kt, and you solve it, usual techniques, and what do you get? You get v of t equals to minus g over k plus some constant e to the minus kt. It's kind of cool. As t goes to infinity, this goes to 0, and your velocity goes to minus g over k. That's a terminal velocity. That's where the basically, in some sense, the friction force of the water balances against the gravity force. If you want to look at, if you could go back to the start and take this minus kmv term over to the other side, or excuse me, like I already did that actually. This was on the other side in the original problem. So when these two things are equal to 0, that's when you get the terminal velocity, which is like the acceleration being 0. You guys know terminal velocity, right? Like you see that idiot jump out of the plane without a parachute the other day? Yeah, he reached the terminal velocity and then he jumped in that 100-foot square from like 25,000 feet up? How far is he up? He was way up there. It'd be much more dangerous if he jumped from a lower height, obviously. You guys don't know this? There's some guy who jumped out of a plane without a parachute and hit a net, like last year. Yeah.
How was this year?
This year, sorry. Excuse me. This is a more complicated raindrop problem. And then finally, what I wanted to end with today, there's a rocket problem, and again, another variable mass problem. I think this one's kind of cool. If you have a flexible rope 4-foot long, 3-foot coiled on the edge of a balcony, you can solve this as a variable mass problem. So like the mass is the mass per unit length times x, the amount that's fallen over. And so you get this differential equation, lambda dx dt v plus lambda x dv dt equals lambda xg. This is just like force of gravity pulling the chain down is proportional to the length that's actually hanging over. And you end up needing to solve this differential equation. And this, actually, you need the special integrating factor technique that I haven't talked about here explicitly. You end up needing to use v squared over x. And I mean, the m is this, the n is that. And through the technique in the book that I'm still waiting for it to come, you end up with a particular integrating factor of, actually the integrating factor ends up being x squared. And when you multiply that, it becomes exact. And there you go. The velocity is the square root of 2g over 3 times parentheses x cubed minus 1 over x squared, where x is the amount of chain that's fallen off the table. And so, I don't know, that to me, the fact that you can solve a problem like that, you can actually describe how fast a chain is falling off the table, and according to how much has already fallen, you can actually solve a problem like this in like a page of algebra. To me, is just fantastic. It's hard. I hardly believe that you can do it. Honestly, it just seems like such a complicated problem. The way the chain is falling, like the more of it's hanging over, the greater the force, and it's rather complicated how that works. Anyway, this is actually I stole from Edwards and Penny's, but anyway, I'll shut up, guys, and I'll see you next class. And if you have, oh wait a minute, homework. Yes, turn me a homework, right? What homework due today? Yeah. So please leave me your homework. With that, I'll shut up. Excuse me. Let me just make a stack in the back if you want, or in the front, whatever. Thank you. Let's see. Should I put the shades back up? Let's see here.
They must know our rights predomination.
That's right. Keep it secret. Keep it safe.
Your problem 6 here?
Oh, I forgot to say, I guess it's still working? Oh, good, it's still working.